is 0.45 feet squared times 2.56, no units, and the final answer will be an area, I'm going to move down to this end of the board, an area of 0.11 feet squared. As I mentioned, this is probably a lower limit, and that's a pretty small area of rudder. That's about 3 inches by 3 inches, a little bit bigger than that, for a boat that's 6 feet long. Okay? We're going to do this equation, or we're going to do this calculation again using the other method that's included in the guidelines, and you'll see that the answer is going to be somewhat larger. In general, if it were me, I'd trend toward the larger rudder, but you're going to sacrifice some speed for the larger rudder, and in fact, when your rudder gets too large, it starts to actually hurt your maneuverability, and we'll see that when we do the next calculation. It's time to go ahead and do the maneuvering calculation a different way so that we can get a little more of a conservative answer, an answer that will give you a little bit better performance than the way we just calculated. This method is a little more challenging because it's not a straightforward equation. You're actually going to have to read some data off of a plot, and we'll go over how to do that in a minute. But the first step that we need to do for this calculation is to come up with a block coefficient. I'm going to use the same dimensions that we used previously, a length of 6 feet, a beam of 1.5 feet, and a draft of 0.75 feet. But in order to calculate the block coefficient, I'm also going to need to know the weight. So we're going to assume the weight of our hull is 100 pounds. Just because it's a nice round number, it's probably going to be pretty far off from what you come up with, but just for the purposes of this illustration is what we'll use. The weight of your payload is going to be 200 pounds. We know that this is a fixed number. This is 200 pounds of sand. Okay? And let's have a weight of a propulsion system of 30 pounds. So that the total weight of our ship is going to be 330 pounds. Now we can convert this weight into a displacement by dividing out the density of water. Remember Archimedes' principle, the weight of your ship your ship will be in equilibrium when its weight matches the water that it displaces. So we'll take 330 pounds and we're going to divide it by the density of water, the mass density of water, which will be 62.4 pounds per cubic foot. All right. Pounds will cancel if they're in the numerator, and because the denominator, this is in the denominator of a denominator, when we work out this calculation, we'll find out that our volumetric displacement is going to be equal to, and I have this number, 5.3 cubic feet. All right. This is how much water our boat will displace if it has these characteristics. Okay. Now let's turn this number into a block coefficient. That equation, block coefficient, is going to be equal to the volumetric displacement divided by the length times the beam times the draft. So it will simply be 5.3 cubic feet divided by 6 feet times 1.5 feet times 0.75 feet. You'll notice we have feet cubed and 3 feet in the denominator so that all of the units will cancel. When you come up with your final block coefficient, you find that the answer is roughly 0.8. And this is going to be important for the next step. Okay? The next step, as I would do it if I were doing this calculation, is to look at this series of plots. We call them nomographs. All right? You have a copy of these in your guidelines. You'll see that here we have 3, and they are for different block coefficients. We know what our block coefficient is for this design. It's 0.8. So we'll look at the plot that's representative for 0.8. Now we'll look at these family of curves in this plot. Okay? They are for different rudder deflections. We have given you in your guidelines that your rudder will be deflected to 30 degrees. And that's going to be the same for all the designs. The only line you need to look at is the line for 30 degrees. Okay? Along this axis, you'll see the turning diameter divided by ship length. You want that number to be as small as you can. That will basically mean your boat will turn the tightest. Okay? So you want to look for a 30-degree curve on the block coefficient of 0.8 and find out where it's the smallest. Okay, I can read this line and find out where the smallest is, and it comes out at a value along this axis of about 45. Okay, so we're going to use that number, 45, in this equation, 1 over a prime t. All right. Next, I'm going to show you what you do with that term and how you can convert that term into a dimensional rudder size for your boat. All right. Remember, we just calculated 1 over a prime t equal to 45. Okay. We extracted that from our nomograph. First thing I'd like to do is flip this around so I know what AT is, not 1 over AT. Okay? So we'll say A sub t prime is going to be equal to 1 over 45. We can do this by basically bringing the A over to this side and bringing the 45 into that denominator. And since I haven't written that down, let's do it together. 1 divided by 45 is 0.022 repeat. Okay. And this is a non-dimensional unit. There are no feet squared. There's no other number or units associated with this term. Okay. In your guidelines, you'll see that there's a relationship between the area of your rudder and the non-dimensional area that comes from this nomograph. Okay. And it's dimensionalized by multiplying this number by your length squared. All right. So what we're going to do is we're going to say our actual dimensional area is going to be equal to AT prime times length squared. In our case, length is 6 feet, and A prime is this number. So area of our ship's rudder is going to be 0.022 times 6 feet squared. Okay? When you work that out, you'll find out that the answer is 0.8 feet squared. So this would be a rudder that's roughly 8 inches long by about a foot deep. Now that's a pretty big rudder, all right? But you'll notice that this rudder was sized for the best maneuvering for this type of block coefficient. You have to realize that all of these types of equations are just approximations. The hull design is actually going to be pretty important to how you maneuver as well. So you can't take this to the bank that if you have this rudder area, you're going to go do this particular maneuver. But it's a good rule of thumb, and I think it will help you do your design. Also remember, the first time we did this calculation with the other equation, we found an answer that was 0.1. So this is 8 times larger than the other equation, which was a minimum, as was stated. So keep in mind that you probably should be somewhere between the first equation, the 0.1 answer, and this answer, the 0.8 square foot answer, for the size of your rudder for a ship with these dimensions. Now, of course, you'll be doing this multiple times as you go through your design spiral and these dimensions change. But it's a good rule of thumb, and hopefully it will get you well on your way to winning the maneuvering portion of your competition. Good luck.